Hello, this is Alfonso Landaverde. I'm back for this again because I keep making dumb mistakes in my presentation, but that's okay. So let's get back to where we were, which is the start now because I'm redoing it. So we have here on the left side, we have my little work that I want to check. And then on the right side, we have the stuff that I'm going to demonstrate to you, which is using this and CalcPlot 3D to graph the quadric surface function, create a contour plot for it, and then create a tangent plane to it. So let's go ahead and get started. We can use function z equals fxy to get the job done because our little quadric surface uh, is 1/2 x cubed minus y cubed plus 4xy. And boom, then we get this. And to show that this is the appropriate viewing size, we can go ahead and zoom out and show that this shows us some more interesting stuff at the cost of my computer fans beginning to blare. But this kind of, I don't know, maybe I'm not a math expert, but it no longer shows anything more significant other than the fact that this is the one portion of the graph that is significant. Like nothing else is changing. And if we zoom in more than the hyperbolic paraboloid like once, like their little thing for it, we begin to lose a lot of these significant features. So until it darn near looks like a straight line. Or not really, but then you keep going and yeah. So we'll zoom out to what they thought was a very satisfactory zoom out, which I agree with. So now we have this. If we could stop right there for a moment, we want to create a contour plot for it. So using CalcPlot 3D, you can actually do this very free and easily by just clicking this button. And it gives you little estimates that it likes to throw out. And I agree with them. This C is kind of like our Z value because it will show the height of or just what the value for Z is at those points. So we'll go ahead and just create the plot. And so this fulfills the requirements on the thing, but let's talk about what it does. It has given us the 3D image showing us the XY plane from the Z axis perspective. And then you can see the elevation changes from that being 1, 0.8, 0.6, 0.4, 0.2, and 0. And so I've experimented before, not on this one yet though, so let's go ahead and do that. Where we've experimented and seen that when we, hold on, let me remove this and go back to it. Create curve. When we reduce the lines in it, so let's just do the minimum requirement of 6, we begin to lose a lot of the interesting features. Like, as you can see that it's going inward here and outward there. Or we can see the parabolic and hyperbolic shapes. But, well, you just can't see them as good. If we were to do 20 and create the plot, we get a very good image that shows us exactly where this thing is going. You can kind of see the hyperbolic like trend of it not wanting to touch these elevations of Z. Because that's kind of what it is. It's just like let me turn off this plane for right now. It's just like it's not touching the hyperbolas from the Z perspective, you know? And then you can also see kind of some parabolic shapes, which just shows the contour plot just does a pretty darn good job of illustrating how it's a hyperbolic paraboloid. But yeah, okay, let's get back to it. So now we need to graph a tangent plane to this at the point 2, -1, -3. And to do that, let's take this back to here. And I don't know why, but now I have this really pretty holographic image. And we're just going to leave it like that because that's the source of me restarting the video 2 times. And I don't think it's that important anymore. But if you'd like, we can do this one. So I'll just actually X this out and do the rest of the work on this one because they're at the same point. Why not? Like if the grid lines are that important to me to restart the video multiple times, I'll do it like that. So we are to graph the tangent plane at the point 2, -1, -3. To do that, we have to find the tangent plane at 2, -1, -3. And that's where I've thrown notes into Desmos because I wasn't going to try and find a camera set up to get this to work like in person. But we have our original function, which is fxy equals 1/2 x cubed minus y cubed plus 4xy. And to find the tangent plane of it, we need to start taking some partial derivatives. So we take a partial derivative with respect to x, which would be 3/2 x squared minus, this becomes 0, plus 4y, because 4y is a constant with respect to x. And then, so yeah, you get 3/2 x squared plus 4y. And then for the partial derivative of y, this is a constant, so it dies. And then we have -3y squared plus 4x, because that is the constant with respect to y. And now we plug in the point 2, -1, -3, and 2, -1, -3, and we get 2 and 5. And so now we have two gradient values for x and y, respectively. And now we need it for z. And to find that value for z, we're really just looking for z naught. Because fxy equals this is the same as writing z equals that. So we go and plug the point in to try and find z naught. And we find z naught equals -3. Because you have, if we want to run through the numbers, we have 2 cubed, which is 8. 8 over 2 is 4. 8 over 2 minus -1 cubed is -1. So 4 plus 1 is 5, plus 4 times 2, which is 8 minus 8. So 5 minus 8 is -3. And so now we plug that into the plane equation. And you'll notice it is an uglier equation. So we set it up in a format that's really nice for Calcplot 3D, which is just z equals. And then we throw that back in. So we have z equals -3 plus 2 x minus 2 plus 5 y minus 1. And then, boom. Except I think I messed it up. Let me grab it. -3 plus 2 x minus 2 plus 5 y minus 1. That's what it was. Plus 1. Boom. Okay. And now how do we know that that's the tangent line at that point? Pretty darn easy. We plug the point in. Sorry, I'm just doing one last double check because that initial mess up scared me. So we grab the point. 2, -1, -3. And that point appears here. And then as you can see where that point is, that sheet is darn near tangent to it. Like, I don't know what more you'd want from me there. That is a tangent line if I've ever seen one. Okay. You should demonstrate that the plane is tangent to the surface. Yeah, I don't know how to, other than mathematically and visually. I mean, those are the two ways that I can think of it. Maybe I can do a further zoom out and show that at that point it's still... Ah! See, this is why this viewing window sucks. We're going to go back to being closer, because being closer actually shows us. I mean, like, this would be the preferred one. Right at the edge, this point, we did this on purpose. This point is, like, right near the edge of the friggin' diagram, so you can easily see it. You go here, and it becomes uglier. Okay. Good job, Mr. Lehman. Kudos to you. But yeah, that little point there does it. And so we have graphed the function with the appropriate viewing angle, and we showed that. We created the contour plot and showed how Calcplot 3D does it really easily for us. I mean, like, there's not much else to say on it. It's really nice. It has your labeled z values, and it creates enough lines automatically to where you get a very good image that shows you the significant features of the graph, being that it goes here, goes here, goes here, and goes here. And then graph the tangent line at the point that and demonstrate that the plane is tangent to the surface. Yep, I think that's all done. So There we go. Thank you. Sorry this one was a little more lengthy. I don't know, wanted to do good or make sure it was explained thoroughly. Have a good one.